remaining portion of chapter 6 applications. We went over one in class, including the differential equations of second order differential equation representing the spring applications with damping and no damping. So I'll start off by reviewing one more time the equation, the elements that creates the equation of the spring applications. And then the goal today is to start off with one example that is a case of no damping, expand this to another no damping application, but where some other elements such as the frequency, the phase angle of motion, the amplitude will be computed, and then transition into the last example where a differential equation of representing the spring applications will be part of it, but design a little bit different. So let me go ahead and then share our lecture notes. You got a copy, hard copy of the lecture notes today. This is actually chapter 6, not section 6.1. When I uploaded, I fixed the name of the file to include all the sections. So this is 6.1, 6.2, 6.3. Now, before we start with this example for question 1 of your homework assignment, let's go over and then review one more time the spring second order representing the spring applications represented by the second order differential equation, homogeneous of the form m u double prime plus gamma u prime plus ku equals 0, where u represents the displacement, it's a function of time, u of t, m represents the mass, gamma is the damping coefficient. So if the second term is not present into the given equation, that means it's a no damping case. And K is the spring constant, which will be computed using the Hooke's law. I remember one of you asked me, where do I get this information? This is all formulas from physics. And then Hooke's law is part of physics formulas. So we'll take those formulas from physics applications. So what is the application that we are dealing with? We have a spring with natural length of 0.5 meters. So this is the natural length. Has length 50.5 centimeters with a mass of 2 grams suspended from it. So the natural length is 0.5 meters, but then when a mass of 2 grams is suspended from it, then that length becomes 50.5 centimeters. Now the mass initially displaced 1.5 centimeters below equilibrium. Now this below equilibrium must be considered when we do compute the elements. So below, we have to represent the word below by using a negative sign. So we'll get into it. So the mass is initially displaced 1.5 centimeters below equilibrium, and then of course released with a 0 velocity. Our goal is to find the displacement. So in other words, to find u of t. So what are we identifying in this case? We recognize this case as a no damping case. So therefore the gamma coefficient is equals to 0. Then the equation becomes the reduced form m u double prime plus k u equals 0. So therefore, the only two constant coefficients are related to mass and the constant, the spring constant k. So let's start off by working with some elements that we really need to generate the coefficients of the characteristic equation. It is given that the natural length of the spring is 0.5 meters. Then due to the mass of 2 grams, then the length becomes 50.5 centimeters. So let's find that delta L stands for the change of length of it. So the difference or the change of length, which we call it delta L, that's going to be the difference between what is the new length after placing the mass of 2 grams, and then versus the natural one. But notice the difference between the units. So you cannot compute delta L unless the units are adjusted. So we are going to change the units all into centimeters, knowing that 1 meter equals to 100 centimeters. So therefore, 0.5 meters will be converted into 0.5 times 150 centimeters. So that delta L, the difference between the natural length and the new one, so the new length and the natural one, is 0.5 centimeters. So it's 50.5 centimeters minus 50 centimeters. So that's 0.5 centimeters. Now, the other element that is important for us is the acceleration due to gravity. The Hooke's law includes the mass, the acceleration due to gravity, that's the weight, by the way. So this is the formula I used in class, K times delta L. So I use W for the weight, where weight is given as the product between the acceleration due to gravity times the mass. The acceleration due to gravity in meters per square second is given as 9.8 meters per square second, but converted into centimeters is 980 centimeters per square second. So now I see a typo in there. I don't know why I multiplied this by 50, because it's 50.5 minus 50, that's 0.5 centimeters. So that should be a 0.5. I hope I did not mess up. And then if I did, please feel free to make corrections, which I can easily make it by uploading yeah, there are no mistakes. So I used 0.5. That's good. That's by accident. So just this 50 is supposed to be 0.5. And then I actually, in my computation for K, I used 0.5. Wonderful. So make sure to change that 50, which is done by accident, into a 0.5. And then I actually used 0.5 in my computation of K, which has no impact overall into my equation. And then I can place the updated version of it in Brightspace. I have to save this as a PDF before I update it into. Okay, so now we transition into. Okay, let me go back. This is what I was sharing. Hopefully this is still recording. Yes. So to find K, I'm going to divide the product between 2 and 980 with the 0.5. 2 times 980 divided by 0.5 is 3,920. So that's going to determine K. We already know M is 2 grams. So therefore, we substitute them to create the characteristic equation. So the characteristic equation is 2U prime plus 3,920U equals 0. I'm using Y. I don't know why I'm using Y, but that's okay. It's the same thing. So the characteristic coefficients are A2, damping coefficient B0, and then C equals 3920. So therefore, AR squared plus BR plus C equals 0 is 2R squared plus 3920 equals to 0. As I said, solving the quadratic equations can be done in different forms. I will continue to use the discriminant and then the quadratic formula. So b squared minus 4ac is 0 squared minus 4 times 1 times 3920. Why have I have all these typos? No, this is so what I did first, I divided by 2. Now I see what it is. I divided by 2 to make the coefficient 1. And then after dividing by 2 to make the coefficient of r squared 1, then I use b squared minus 4ac. So that's why you see 1960, because 3920 is divided by 2. So 0 squared equals negative 7840, which is obviously less than 0. Then we know we have two complex solutions. We get R1 and R2. So R1 is going to be 0 minus the square root of negative 7840, which negative sign is replaced by I square. And then 7840 is not a perfect square, but can be split up into 784 times 10, where 784 is a perfect square and the square root of it is 28. So we get negative 14 square root of 10 I. So therefore, lambda is 0 and omega is 14 square root of 10. Once we generate lambda and omega, we write the equation. So the equation is defined by e to the power 0 times C1 cosine of 14 square root of 10t plus C2 sine of square root 14 square root of 10t. Now I'm about to use the initial conditions. The initial displacement is negative 1.5 centimeters. Why negative 1.5 centimeters? Remember I mentioned below equilibrium. This is where that below is applied. And then there's no velocity, so that means velocity is 0. We know the velocity is the derivative with respect to time of the displacement with respect to time. So that means for time 0, y prime is going to be 0, or the u prime will be 0. And for t0, the displacement u of 0 is going to be negative 1.5. So we apply the initial conditions into the first formula, which is the formula for the displacement. So we replace by negative 1.5 and then the time by 0. So we have C1 cosine 0 plus C2 sine 0 equals negative 1.5. We know that sine 0 is 0 and cosine 0 is 1. So therefore, C1 is negative 1.5. And then in order to use the second initial condition, we have to differentiate. So this is the derivative of the displacement equation. So if we differentiate cosine, we get negative sine. So that's why you see negative C1. But because of this 14 square root of 10, we have to differentiate 14 square root of 10t. So that's why we pull out this coefficient in front of it. So negative C1, 14 square root of 10 sine of 14 square root of 10t plus C2, 14 square root of 10 cosine of 14 square root of 10t. And we substitute t by 0. And then we set this equals to 0. So therefore, the final equation, since C2 is 0, that is going to eliminate the second term. So the final equation is negative 1.5, which is C1, cosine 14 square root of 10 t. And then I hope this is for t positive. And then I hope this is understandable for all of you. Now we're going to run another application with no dumping, almost a very similar equation. But what is different now, there are some new elements that we are going to compute that are not part of any of the applications of related to the spring problems. So we have a 10 kilogram mass stretches a spring 70 centimeters from equilibrium. Suppose a 2 kilogram mass is attached to the spring. The initial displacement is 25 centimeters below equilibrium. And given an upward velocity of 2 meters per second, we're still finding the displacement for t positive. Now this is what is different. You notice that it's almost the same application. So that means we are using the same equation. But what is different now? We are computing some brand new elements: the phase angle of motion, the amplitude, the period, and the frequency. And then, if you all recall, during the class time on Tuesday, I did a quick review, a refresh of these elements from your pre-calculus 2 classes, pre-calculus 2 and trigonometry classes. I did review the elements of the complex polar system, the real axis, the imaginary axis, the A and the B, how we compute the tangent of the central angle theta. So all these elements that are so important. Now we need that for what I'm about to compute as far as these brand new elements of the spring application. Let's run the equation first so we can get the coefficient, get the displacement equation, and then we'll get to the elements afterwards. So this application can also be modeled by differential equation of the form m y double prime plus ky equals 0. You can use u. I don't know why I'm using y, but that's okay. It's still the same thing. We know that m stands for the mass and k for the spring constant. The spring constant must satisfy the following equation, which is the Hooke's law. The W, the weight, is equals to K times the difference of the length of the spring, or delta L. And then the weight is computed by the product between the acceleration due to gravity times the mass. Now the acceleration is 9.8 meters per square second. And then the mass is 10 kilograms. So we are going to change delta L. There's no information for the natural length. So therefore, whatever that new length is, that's going to be delta L. And then it is given in centimeters. We know 1 meter equals 100 centimeters. We divide by 100 to convert it into meters. So we have 10 times 9.8 equals K times 0.7. And then K is 10 times 9.8 over 0.7, which is 140. So K is 140, M is 10. We substitute them. So the equation becomes A is 2, B is 0, C is 140. Why is A 2? I don't know. A is supposed to be 10. Wait a minute. What am I doing? I think M is 10. Oh, suppose 2 kilogram mass is 2. Yeah. And then another typo. So I'll save it later on and convert it into a PDF before I upload it. So we have A is 2, B is 0, C is 140. We make the coefficient equals to 1 by dividing both sides by 2. So we get R squared plus 70 equals 0. B, the damping coefficient is 0. So B squared minus 4AC is going to be 0 minus 4 times 70. So that's negative 280, which is 280 I squared. Two complex solutions. 280, we can convert it into 4 times 70, where 4 is the perfect square. So we get the 2 out after taking the square root of 4. So negative 2 square root of 70i over 2, which is negative 70i, square root of 70i. So omega is square root of 70, and then lambda is 0. And then we write the displacement equation as a C1 e to the power 0, C1 cosine of square root of 70t plus C2 sine of square root of 70t. Now we are about to use the initial conditions. Initial displacement is 25 centimeters. If I divide it by 100 to convert it into meters, it's 1 over 4. And then the velocity in this case is 2 meters per second. So velocity is the derivative of the displacement over time. So therefore, we have, if time is 0, y of 0 is 1 over 4. And then if time is 0, y prime of 0 is 2. So let's start substituting. In the first form, the displacement equation, we have C1 cosine of 0 plus C2 sine of 0 equals 1, 4, where cosine of 0 is 1. Sine of 0 is 0. I apologize. So after eliminating the second term, we get C1 equals 1 over 4. Now, the reason why you see the minus, because this is below equilibrium. So let me share again. Something happened with the sharing. There you go. Because this is below equilibrium, that's why you see the minus in front of it. So there's nothing wrong with the minus sign. And now we differentiate the equation of the displacement. Sign, if it is differentiated, it generates a negative sign. And then, of course, the square root of 70, because you don't have t alone, you have square root of 70t. So using the chain rule, you have to differentiate square root of 70t. So after we differentiate, we substitute. And then we have the first term will disappear because sine of 0 is 0. The second term, cosine of 0 is 1. So we get C2 square root of 70 equals 2, not 0. There's another typo in there. No, right there. Cosine of 0. So you're not thinking that it's a 0. Cosine of 0 is 1. And then, therefore, this product is going to be C2 square root of 70 equals 2. So that's C2. So the displacement equation is given in this form. Negative 1 over 4 cosine square root of 70t plus 2 over square root of 70 sine square root of 70t for t positive. Now, let's get the elements. If you recall what I did in class, these two elements, C1 and C2, are indeed representing the coordinates of the point in the second quadrant, because x, or the real coordinate, if I call it, is a negative number, and then the other coordinate is positive. So as a second coordinate, as a second quadrant element, we are going to make sure that when we generate the phase angle of the motion, we are taking in consideration that this is a point in the second quadrant. So what we do to find the elements, if the displacement equation is given in this form, and then C1 and C2 are given by respectively negative 1 over 4 and 2 over square root of 70, then the amplitude, big R, is computed as the square root of C1 squared plus C2 squared, where each one of those coefficients, C1 and C2, is defined by R cosine of phi and R sine of phi. So this is the order pair that I was referring to that belongs to the second quadrant. Now, cosine of phi is C1 over R, and sine of phi is C2 over R. Knowing that R is the square root of C1 squared plus C2 squared, each one of them becomes C1 over the square root of C1 squared plus C2 squared. Why we need this information? Because this is how we compute the phase angle. So we use tangent, which is the ratio of sine phi over cosine phi, and then eventually becomes the ratio of C2 over C1. So tangent is going to be, after going over the computation, it's going to be -8 over square root of 70. And then in order to get phi, you have to use tangent inverse. So you get the answer -44 rounded, because this is not exactly -44. But I want this angle to go to the second quadrant. So to move the angle into the second quadrant, first I'm going to move it into the first. So the -44, which is in the fourth quadrant, clockwise measured from the initial side, which is on positive x-axis. I have to measure counterclockwise 44 degrees, starting off with the initial side on the positive x-axis to go to angle 44 in the first quadrant. And then to reflect this into the second quadrant, all I have to do is add 90. So therefore, the corresponding angle of -44 in the second quadrant that fits the given coordinates C1 and C2 is 134 degrees, and that's the phase angle of the motion. Now, remember the amplitude is the square root of C1 squared plus C2 squared. So if we compute the amplitude, we are squaring -1 over 4 and 2 over square root of 70. So -1 over 4 if you square it is 1 over 16, and then 2 over square root of 70 if you square it is 4 over 70. If we find the least common denominator, we get 67 over 560. 560 is divisible by 16, so we get 4 out, and then keep square root of 35 after rationalizing. We get square root of 2345 over 140. So the amplitude rounded to 2 decimal places is 0.35. And finally, we need to get the new period. And the new period is computed by using the old period of cosine and sine. These are both periodic functions of period 2 pi. The period is, for you all to understand it, is the length of one cycle. And then one cycle is a full rotation from 0 to 360. This is all going back to precalculus and trigonometry. So in order to find the new period, we always divide the 2 pi, the old period, by the frequency of the motion, which is the omega 0. The frequency of the motion is computed by the square root of k over m. Again, these are all physics formulas. So if k is 140 and m is 2, I guess, not 10. I don't know why I'm using. Then the frequency of the motion is square root of 14. But again, I have to. Yeah, so the initial mass is 10. So the omega 0 is square root of 14. So that's going to make our period to be 2 pi over square root of 14. After rationalizing the denominator, it's 2 pi square root of 14 over 14. And now let's transition to number 4. That's another example using damping, but it is designed a little bit different. So what is different now? A mass weighing 56 pounds stretches a spring 8 inches. The mass is in a medium. that exerts a viscous resistance of A pounds when the mass has a velocity of 6 feet per second. Now, what we need to do, we don't need to solve the equation in this case. We need to find the value of A. So for what A, value of A, will the system be over-damped? Remember what the conditions are of damping and then the 3 types of damping that we discussed in class. We have under-damped. Under-damped means the system still oscillates, but the amplitude gradually decreases. So this is more like verbally explaining. Now you know what the amplitude is the uppercase R, which is the square root of the coefficients C1 squared, C2 squared. These are the coefficients of the displacement equation. So the system in this case still oscillates, but the amplitude gradually decreases. So we are expecting this discriminant gamma squared minus 4mk to be less than 0. And this is the equation. Now we have critically damped where the gamma squared minus 4mk is 0. The system returns to the equilibrium as quickly as possible without oscillating. And the solution is defined in this case by displacement equals C1 e to the power RT plus C2 T times e to the power RT. And then we have the one that we need, the overdamped. The overdamped, the system returns to the equilibrium slowly without oscillating. So this is where the discriminant is positive. Now I need to determine the value of A such as the system is overdamped. So for the system to be overdamped, this has to be satisfied. So let's look at this. To determine for which value of A the system is overdamped, we need to model the system as a second-order linear differential equation of this form, with damping, which is the general form being mu double prime plus gamma u prime plus ku equals 0. We do have a weight of 56 pounds. We do have a stretch of 8 inches. I have to divide 8 by 12 to convert it into pounds. So that's to convert it into feet, which is 2/3 of feet. And then we have a vicious force, which is A. A is the one that we are going to determine when the velocity is 6 feet per second. So to determine the mass, we are going to use the physics formula from the Hooke's law that the weight is W times the gravity. Gravity in terms of feet per second is 32 feet per second. And then the weight is 56, so 56 divided by 32, so that's 7/4 slugs. Now determine the spring constant using the Hooke's law. The spring force equals the weight when stretched. So this is K times 2/3. Remember, that's the stretching. It was given initially as 8 inches. We convert it into feet. Equals the weight, which is 56. This was M times G, by the way. So K in this case equals 84 pounds per feet. Now we are going to determine the damping coefficient. Remember, the force of displacement equals the damping coefficient times the stretch. In this case, the gamma which is the damping coefficient, is going to be equal to A, we don't know A, divided by 6. So this is our general equation. Mu double prime plus gamma u prime plus ku equals 0, where u is the displacement, a function of t. Now we need to know for what values of A the system will be overdamped. So I'm going to substitute the coefficient. The coefficient M is 7/4. Coefficient gamma is A/6. And then coefficient K is 84. And then I don't need to solve the equation. All I need to do is check the condition of overdamping, which has to do with the discriminant of this characteristic equation. So in other words, gamma squared minus 4mk has to be greater than 0. So gamma squared is A squared over 36, and then 4mk is 588. You multiply 4 by 7/4, which is 7, by 84. So A squared over 36 minus 588 is greater than 0. I multiply both sides by 36. So I can eliminate the 36 in the denominator. I get A squared greater than 21,000 2168. So therefore, A is greater than the square root of 21,168, which is 84 square root of 3, approximated to 145.49. So the system will be overdamped for an A greater than 145.49. And finally, our last application has to do with the RLC system, circuit system, known as the steady state current applications. Again, we are focusing on a homogeneous case. The general equation for the steady state current in a circuit of the form RLC, and then I'll go over what the initials stand for, is given as L Q double prime plus RQ prime plus 1 over CQ equals to 0. So what is this particular system? What are all these elements? The system is known as the RLC circuit. There's a reason why. R stands for the resistance measured by ohms. Now the resistance in given equation is 6. Resistance is the coefficient of Q prime, and then we'll get to what Q prime is in a minute. L, which is the coefficient of Q double prime, is the inductance. This is measured by Henry's. L is 1 over 10. C stands for the capacitance. This is measured by farads. C is 0.004, but the coefficient K is defined as 1 over C. So if you divide 1 by 0.004, you get 250. So that's why you see 250 in front of K. Now, what is Q? Remember, we are solving this in terms of Q. Q is known as charged. This is measured by coulombs. And then the rate of change of coulombs, which is the charge over the time, is what is known as the current. So the current is nothing but the Q prime. We write the current by I, and then this is measured by amperes. So now if all these coefficients are substituted, then we have to multiply by 10 to eliminate and make the coefficient of Q double prime equals to 1. And then solve this brand new equation, which is Q double prime plus 60 Q prime plus 2500 Q equals 0. So notice that the characteristic equation is R squared plus 60R plus 2500 equals to 0. Obviously, it is the discriminant B squared minus 4AC is negative 6400. That's less than 0. So therefore, this is going to be a complex root case. And then as a complex root case, we find R1 to be negative 30 minus 40I, and therefore R2 is negative 30 plus 40I, where lambda being negative 30 and omega being 40. So in this case, the charge Q of t is measured by using the equation e to the power negative 30t times C1 cosine 40t plus C2 sine 40t. And that's all I have for the applications. I had a few typos in there. I'm gonna save this new copy. And then, of course, I will update the version, the new version with the typos I had in there. Normally, when you type in, there's always a possibility for a few errors. And then, as always, I apologize for my few errors. But now the new copy will be uploaded in Brightspace for you to see it. Okay, so this is where I'm going to stop the recording, and then this video will be posted for you to see it so you can get the work done. This work is due this Sunday before midnight. Okay, enjoy and have a nice weekend. I'll try to grade the exams over the weekend. I will do my best. Hopefully, I will have a full recovery and then have the time to fully grade the exams over the weekend. Have a nice evening, and then I'll see you on Tuesday. Now we are getting close to the final weeks of the semester, still 2 weeks remaining for classes. So we're going to focus only on chapter 8. And then if time allows us, we'll get to chapter 9. I don't know. We have to see. The other thing I'm going to do is I will work with a study guide for the final exam and then have them ready, have the study guide ready and the solution sometime next week. Um, at least have the study guide first, okay? But I have to work with the notes for chapter 8. That's going to be the priority. If we do not have time for chapter 9, then unfortunately we are going to skip 9, but we'll see how that goes. Okay. Bye-bye.